This chapter shows how to measure and control the flow of solids or liquids in an industrial procedure. Look at this complex drawing and notice how the pipes begin to resemble wires in a schematic circuit. And just as in electronics you must control current, here in this industrial procedure you must control the flow of liquids. There are two ways of measuring flow. In the case of liquids, you measure in the terms of volume per time. In the case of solids, you measure in mass per time. This slide shows the formula used in our country for measuring solids. A solid would be something like gravel, sand, powders, and other types of similar materials. The measurements that results from using this formula are known as inferred measurements. Inferred because we don't directly touch the material. Instead, we depend on the weight per time. This slide gives us a better idea of what we mean of weight per time and how we can measure powder by how much it's going to go past a certain point and how much it weighs to give us an idea of the flow. The Reynolds numbers is used to describe the flow of a liquid, but the liquid could be inside a pipe, but it could also be in an open container such as an aqueduct. And see, the Reynolds number consists of several parameters which are then used to describe the type of flow that we have. Imagine that you have water flowing through a pipe or else an aqueduct, and as the amount of water is small, then the water flows smoothly along the bottom, and this is called laminar flow. As more water flows in the pipe or aqueduct, it begins to slow down along the edges and move smoother or faster towards the center. And this is called transition flow. Now let's say we have a huge amount of water flowing, and now the water becomes turbulent, as you can see from the drawing. In this case, it could do some serious damage to the pipe or to the aqueduct. As you can see, it'll cause stress on all the sides of the pipe. Here are some methods for measuring the flow through a pipe, and these are based on Bernoulli's principle, which says that the pressure will change depending on the speed of the liquid. And these are inferred measurements because once again, you're not touching the fluid, but you are measuring something else. In this case, you're going to be measuring the change in pressure. In the rotometer, you have a sample taken of the fluid from a bigger pipe. The liquid will move upwards and lift the float to give you an idea of how much fluid is flowing. In this case, this is a direct measurement because you're actually touching the liquid you're trying to measure. The positive displacement flow meter makes direct contact with the liquid that's trying to be measured. As the more liquid flows through the pipe, then the impeller will turn faster, which gives you an idea how much flow we have. The velocity meter also makes direct contact with the fluid being measured, but it in fact is a little generator where the fluid turns a turbine and then the turbine will turn a small little generator which gives you an idea. The more flow, the faster turbine, so the more voltage come out of your generator, and this gives you an idea how much is in the flow. A Coriolis meters are attached to a bigger pipe and then it'll take a sample of the fluid. Then the fluid will cause the meter to distort, to vibrate. Of course, the vibration must be present inside a magnetic field. It's interesting that one of our graduates worked at a company where they were working with Coriolis meters. And he told me that normally they're very big and they're usually attached to a big pipe, maybe a 4 foot diameter pipe, and it'll take a measurement from a really big pipe. Here's another direct contact device which measures the flow based on the electrode turning inside a magnetic field. But the windings of the electromagnetic field are contained outside the pipe because this device is used when there are dangerous or explosive liquids. In this device, we deliberately create turbulent flow, and this creates the vortices, which then change the pressure, and then the pressure will give us an idea of the flow. So once again, this is an indirect, an inferred measurement, again to be used when the fluids are dangerous. So far, we've been trying to measure liquids that are clean. In the case of liquids that are dirty or liquids that have particles such as paper or other things, then we need another method for measurement. With the ultrasonic flow meter, the amount of particles floating in the liquid will reflect the sound in a different way. The more particles, then the more sound is reflected And this will give an idea of the amount of flow. Again, it could be pulp, it could be some other material floating in the liquid. Here's another ultrasound device used for liquids that are very dangerous or explosive. And here, the motion of the liquids will distort the sound and give you an idea of the flow. Once again, for liquids that could explode. Here's a table for selecting flow meters. And as we said before, the first consideration is it clean? Is it dirty? Is it explosive, corrosive? Does it conduct or not conduct? And these will help you select a flow meter for different applications.